Hello, today I want to walk you through some code, in this case it would be .NET code, to convert RA and declination to altitude and azimuth. Now this calculation is absolutely the fundamental calculation for any kind of star chart application you may wish to write, and you can take an observer's location anywhere in the world and convert the RA and Dec to that observer's altitude and azimuth. Now this code I'm about to walk through has a long history. I started writing this kind of code late 80s, something like that, so a long time ago. A couple of books along the way, absolute classic books. Peter Duffett Smith, this is my book I bought about 1990. It was written in a very old basic. It's kind of sort of BBC micro basic for you who remember that. And this Montebrook book I also bought around about the same time, about 1990, but the algorithms, although they're written in quite an old style basic, full of go-tos and go-subs, the algorithms themselves are still very valid. So obviously I've updated the code I'm about to walk through the years, all the way through various IDEs. At the moment I'm using Visual Studio 2019, but the code I'm going to show you will be easy to translate that into C#, C++, Java, whatever you want to do. So hopefully this will be very useful for any of you that are thinking about writing your own star chart applications. And okay, let's get going. Okay, so just to start, quickly on my website we can download the code, Astro Workbench co.uk, go to software and star charts, and this will show you what you can do when you have the fundamental calculation of RA and Dec to altitude and azimuth at your disposal. You can download that just by going to there and download the zip, a setup file. It will install onto your Windows platform. It will install the .NET Framework 4.8 if you haven't got it, and obviously my application. I don't use any other third party, there's no adverts or anything, so rest assured you're only going to get my code and the .NET Framework. Okay, so just to show you what can be done with once you have this calculation, the classic chart, this is the application that I just downloaded from my website. The classic chart is the planisphere view, which gives you the 360 degrees azimuth and 0 to 90 degrees altitude. And this type of chart takes all the objects that you want to specify. In this case I've got Messier, Caldwell, NGC, all the usual suspects, and it will plot them for your local date time, your local location. I'll come on to the location in a second. So if I just increment the minutes, you can see the objects rising in the east and obviously setting in the west as we go along. Okay, so if you take something like M52 for example, I display the coordinates up here. You can see that at the moment for this given location and date at time, it's about 31 degrees altitude and 27 degrees azimuth. Okay, so that's one classic way of using altitude and azimuth data. The other classic way is using a stereographic projection. Actually, I might do another video on stereographic projection because that's quite key and fundamental as well. So once again, this is a classic way of representing the night sky. I live in southern England, so actually if I just look north instead of south. Okay, so my location is about 51 degrees latitude, and sure enough there's Polaris, 51 degrees latitude. So this again is another classic way of displaying objects by altitude and azimuth. The other thing I do, which also depends, this is all the reference data that I use, so let's look at Messier data for example. So this is just the Messier data, so I take the declination and RA and draw a altitude and azimuth chart here. So as you scroll down it draws a chart which makes it very easy to see what's visible at the moment. Okay, and I do the same for Caldwell and NGC objects. So all of these screens, they really rely on this RA and declination to altitude and azimuth calculation. So let's now actually walk through the code. So this is a test harness. Excuse me. This is a test harness that I use two sets of predefined data, one based in the southern England where I live and one based in New South Wales, Australia, actually just by Sydney, the coordinates I've used. So let's just quickly run this first of all to put the whole thing into context. So what you can see here is that for test set 1 I am using hard-coded parameter values, RA, Dec, local date and time, your time zone. I'm in southern England, quite close to Greenwich, therefore my time zone is 0. Daylight saving is 1 because this is August and that's summertime for UK. And my coordinates, my latitude and longitude are here. I'm just west of Greenwich, so it's minus 1.8 degrees and 51 latitude. This isn't my exact coordinates, my home coordinates by the way, so if you do a reverse geo lookup you won't find out where I live, but it's, you know, it's close enough. So these are the parameters that you need to calculate the altitude and azimuth for any given RA and Dec. So you need the RA and Dec of the object. Declination is obviously negative if the object is south. This is north. I think this is Vega actually. I think it might be Vega. Anyway, local date and time, time zone, daylight saving, latitude and longitude. So these are the coordinates you need. So when I calculate the altitude and azimuth, the results I should get is this. The reason I've also displaying these on this test form is so that if you do tinker with the code, and please go ahead and have a tinker, you'll be able to tell whether you've broken the code by, obviously it won't match the expected value. So let's just do a quick calculation. Yeah, sure enough it matches the expected values as you would expect. So altitude is 55.5 degrees nearly, azimuth is 93.25 degrees nearly. Greenwich time, this is Greenwich mean time actually, 15:37, universal time 17:39. Obviously universal time is only 1 hour's difference from my local time, that's because of the daylight saving, and local sidereal time is 15:29. If I switch to the second set of test data, you see the only thing that changes is all this. I actually use the same RA and Dec. If I just flick between the two, you can see the only thing that's changing is the data down here. So I've got a slightly different date. Time zone is obviously very different for Australia, 10 hours ahead, so time zone is always plus or minus. It's always between 0 and -12 or 0 and +12. Daylight saving, you can actually have half-hour time zones as well. Daylight saving is 0 because July in Australia is their winter, so daylight saving is 0. The latitude -33, so the latitude in the first test was positive because it's northern hemisphere. In this test, i.e. Australia, it's negative because it's southern hemisphere. And the longitude in this particular test is positive. In the other one, if you remember, it was negative because I was just west of Greenwich. But here for Australia, 151. So again, I changed the expected, so you can see what's expected. Do a quick calculation. And bearing in mind this is the same object, same RA and Dec. In Australia, it's actually just below the horizon. It's -1 degrees, or nearly -2 degrees. 317 azimuth, totally different times as you would expect, Greenwich sidereal, universal and local sidereal. I've also put two other things here. So this button just runs it in a for loop 100,000 times. So it took 0.8 of a second to run it 100,000 times. And this is a mid-range i5, Intel i5 PC, nothing special. So you can see that certainly time-wise, you won't be plotting 100,000 items on a chart. Otherwise your chart will be absolutely smothered. So you can see time-wise there's absolutely no problem here. This is a real big stress test for loop. So this for loop, it's two nested for loops. Outer for loop goes from -90 to +90 declination in 0.1 steps. The inner for loop goes from 0 to 24 in 0.1 steps. So it's running, what's that, a few 100,000 times. Most of the time is actually taken because I'm displaying the for loop values. Otherwise it would run very quickly in a matter of seconds. This is a good test because it means if you've got any dodgy calculations such as division by 0, this will expose it. And also it's handy because you can monitor the memory. If you see the process memory going up and up and up, it means you've got a memory leak in your code and something's a bit iffy. So that's just two extra sort of tests I like to put on. So this is a test harness that if you decide to tinker with the code when you download it, you can download this code from my website, Astro Workbench Co UK. You can then run these tests or just run this, and if you don't get the expected values, then you know you've broken it in some way. So let's now walk through the actual code. Let me just stop that. So the actual code, I won't bother walking through the code behind the actual screen because there isn't really anything great to talk about there. It's really a lot of, let me just go up to the top, it's really just some functions to set up. That's the test data one that gets set up, so that's the test data for the first test based in Southern England. That's the test data for the second test based in Australia. And the most interesting function within the code is this one, which is what runs the actual test. So when you click that button, this is the function that gets called. So the code to do the conversion is encapsulated in a class which is in this file, RA Dec to Alt-As. I've got a class called RA Dec to Alt-As, which is encapsulated in that file, which has one public function, public facing function called RA Dec to Alt-As. And these are the parameters you need to send in. So the parameters you need to send in are, as you would expect, those values that you saw on the screen. So you need to send in the RA and declination of the object in question, the observer's longitude, observer's latitude, local day, month, year, local time, daylight saving, time zone. And it returns 5 values: universal time, Greenwich time, local sidereal time, altitude and azimuth. And these are the 5 values that you saw down the right hand side of the screen. Now you may want to tinker with this. For example, one thing I'm doing is that the longitude must be sent in degrees, the latitude has to be sent in radians. Not a great idea to mix your units like that, so you might want to change this so they're both sent in degrees or both sent in radians, and the function does the conversion. The other thing you might want to do, for example, is rather than sending your local day, month, year, time as 4 separate variables, you might combine that into one date time variable and send that in, so you cut down the number of parameters. All sorts of things you can do, but anyway, let's go to this class definition and walk through it. Right, so this is the public facing function we just looked at. These are the parameters we're all sending in, and these are the by ref ones, so these are the parameters that are coming back out. So how do we do it? Let me just scroll down a bit, and as you can see there's very little code here, very little code, so I've split it into some separate functions. First thing you do is you get the local, convert the local time to local sidereal time. Also I'm getting universal time and Greenwich time, as well as local sidereal time. Then convert to an hour angle. What's an hour angle? I will explain that in a minute. And then we're converting from equatorial coordinate system to horizontal coordinate system, and then we return the results. Horizontal coordinate system is the classic altitude and azimuth as an observer on the Earth's surface would see. So that's the basis of all your star charts. So I've broken it into these few functions. So I'll just scroll down and go through each function one by one. So the first function, converting local time to LST, local sidereal time. I'm actually returning 3 values out of here: universal time, Greenwich time, local sidereal time. So the algorithm to do that is that. Now then, as you can see here, there's a lot of magic numbers, and I've described these magic numbers here. It's a well published algorithm to do it. You'll find this algorithm on the web, you'll find it in those books that I showed you. One thing that it does need though is a Julian date to be calculated. Now Julian date has a number of different flavours, and I'll scroll down and go into that function in a moment. But basically you need to get the Julian date for your local date, and then you follow this algorithm and out pops your various times. So your universal times calculated there, mean Greenwich mean time is calculated here, and then local sidereal time is calculated there. So very little actual coding. You see, most of this function is the comments, which you can read through at your leisure, where I've tried to describe most of the magic numbers. Okay, let me just scroll down a bit more. So the Julian date, so there's a number of different flavours of Julian date. It's probably about at least half a dozen, and mainly they depend on which epoch is the base for the Julian date. I use the IAU, International Astronomical Union agreed standard Julian date. As this is an astronomy application, seems like a good Julian date to use. The algorithm for doing this is well published, which again I've put in the comments here, and again I've tried to describe most of the magic numbers you see, but essentially the formula is that. So again, it's very simple, but what you will find is that if you compare the Julian date that this gives out with some Julian date calculator on the web, you'll get completely different values, because the Julian date calculator on the web may be using a different flavour of Julian date, i.e. not the IAU Julian date. So be aware rather, that when you're looking at Julian dates and making comparisons of Julian dates, make sure you're comparing like for like. But anyway, it's a very simple calculation to get the Julian date. The hour angle. Okay, so the hour angle is a point on the celestial sphere using equatorial coordinate system. My best way of describing this is go onto Wikipedia. I have no interest in Wikipedia as far as I don't work for them or have any representation with them, but they've got great diagrams on there, and they've got a great diagram which explains what the hour angle actually is, the astronomical hour angle, what it actually is. So look that up. But essentially, as you can see, it uses Greenwich sidereal time and your longitude. So it's a one-line piece of code. This normalised function is in my utils class there, but essentially just make sure that the resulting figure is between 0 and 24. As you can see, the hour angle is a function of Greenwich time and longitude. Longitude must be passed into this in degrees. So you've got sidereal time in hours, longitude in degrees. You're mixing your units, so you have to converge your units. So I've chosen to turn the degrees into hours by dividing by 15. So 24 hours is 360 degrees, therefore 360 divided by 24 hours is 15, so 1 hour is 15 degrees. So to convert degrees into hours, you just divide by 15. And then you take away the right ascension. So 3 parameters in, 1 line of code, job done. Next function, equatorial to horizontal. Now, once again, I'm not promoting Wikipedia here, but once again, if you go to Wikipedia and look up equatorial and horizontal coordinate systems, you'll see great diagrams, and it's basically trig. It's trigonometry, that's all it is. And therefore, there's 2 very nice cosine rules that you can use to get altitude and azimuth. So these are the cosine rules. So these are the 2 lines of code which implement the cosine rule with a little bit of extra jiggery pokery on the end. And one thing to note here is this is, as you can see, .net. .net trig functions, so sine, cosine, tangent, etc. The arguments have to be in radians. If you put an argument of degrees in, it won't work. You'll get a nonsense figure. So that's another thing to check. Whatever language you're doing, check what arguments you need, whether it's radians or degrees, and make sure you're using, the correct units. And that's it. That's all the functions. As you can see, those functions have got very little code in them. In fact, there's more comments than there are code. So what you could do, again, for an example, if you wanted to, rather than having the main public function here calling out to our functions, calling out to these functions which we've just looked at, you could just take all that code and just put it in one function. I've chosen to split it up because it's a bit easier to understand and a bit easier to walk through. But as you can see, there's very little code, and this is the code that I use in my astronomy applications that I've demoed to you. So please download my application from Astro Workbench co.uk and see if you like it, and download this test harness, which is called AWB RA Dec to out as. You can also download this Visual Studio solution from our website as well. If you're not using Visual Studio, it doesn't matter, because this is the class that you really need, and this class is all encapsulated in this file. Okay, so it's in this file here, which is a pure ASCII text file, so you can open it in any editor. So if you've got a different IDE and you want to translate it into Java, say, you can load this up into your IDE and just go ahead and translate it into Java or whatever. The only other thing you might find of interest is this supporting class that I've called utils. So there's a function here to convert radians to degrees. There's a function to convert degrees to radians. As you can see here, a radian is simply 180 divided by pi, so it's 57.29 blah blah blah. and degrees is the opposite way around, it's pi divided by 180. Okay, and there's some other functions in here. Convert hours, minutes, seconds to a decimal number. This is normalised functions that you saw to get a number within 0 and 24, and that's my very simplistic error handling that I've included in the code. You can obviously improve on that. Okay, that's it. That is the code to convert RA and Dec to altitude and azimuth for any object that has RA and Dec, given the observer's longitude, latitude, local date and time, daylight saving and time zone. And this will calculate for you universal time, Greenwich sidereal time, mean Greenwich sidereal time, local sidereal time, altitude and azimuth. So I hope you'll find that useful, particularly if you're thinking of writing your own star chart application. This is the fundamental thing. Okay, I hope you enjoy it. Please visit my website, Astro Workbench UK, download this, have a peruse, and yes, I will see you next time. Thank you.